So in this lecture, we are continuing the discussion of finding the wave function of a particle that scatters off of a step function or yeah, a, a constant potential energy that is zero on one side and then has some value on the other. So in previous lectures, we worked out what happens to the incident side, the incident particle, or we'll call it the incident wave function, the reflected wave function, and the transmitted wave function. And we worked out focused on the incident wave function, first working out its wave function in terms of time at the start, t equals 0, and then propagating that wave function with respect to time. Now what I want to do is focus on the reflected wave function and the transmitted wave function. So basically, if you remember, the reflected wave function was on this side, and the transmitted wave function was on this side of the barrier. And so what we do is basically considering the case where we can ignore the incident wave function and looking at a time, sometime greater, sometime at t, really large t, t going to infinity. And so to set it up, we basically write out what the incident wave function is, and that's a free particle wave function. So for the incident case, its wave function was the step function in the minus x region, pi to the minus 1/4 power, the width of it plus I h bar t over m to the minus 1/2 power times e to the minus x plus a minus h bar k0 t over m squared over the width, which is 2 delta squared 1 plus I h bar t over m, delta squared again, times the momentum part, which is e to the I k0 x plus a minus h bar k0 t over 2m. So this wave function is the incident wave packet, and it includes the time dependence, so as it's moving through space. So let's incorporate all of the wave packetness into a new function called g, where g is a function of the position, it's centroid minus a, where it starts, its momentum or wave number, and the time. So why did I write it out this way? I wrote it out this way because the reflected wave function should also be a wave packet that's now moving in the opposite direction. So in that case, if we look at it, what we have is a object that moves to the left with a momentum of minus h bar k0. So the same momentum as the incident particle. It's peaked, it's centroid at A, and it has a factor of B over A multiplying it to give it its normalization, the size of which this wave packet has. Since it's peaked at the initial momentum, we can, call this now B over A 0 for its peak, because it's peaked at the incident wave number. So in this case, we can now write out the wave function in a very compact form where we basically just put everything inside this Gaussian function of a minus k times t times b over a naught. So basically, if we look at the what's in it, we have the part that tells us that it's on the left-hand side of the barrier, so at x less than 0. This is the Gaussian wave packet, but it's moving now. It has a amplitude, has a centroid at a, but it's moving with a momentum minus k0, and it has a factor, a normalization factor, which essentially tells us the height. Because if it bounces off the barrier, it may become smaller. Because some of the wave function, some of the, goes into how it's transmitted, and some goes into how it is reflected. So now what we want to do is, since we have that, we can now calculate basically what's called the reflection coefficient, which is essentially kind of like a probability. So R is the integral of that. The reflection coefficient is essentially the probability that it's going to be reflected. So we can put this in, we can integrate, and we get b over a naught quantity squared times g a minus k0t squared dx. So we integrate from minus infinity to infinity. The normalization is just a constant, so we can take it out front. And we now have the integral over our Gaussian wave packet, which, if it's normalized, essentially is an integral is 1. So that means our reflection coefficient is just this ratio of the constants squared. Which, if we plug that in from our previous derivation, then what we have is square root of E naught minus the square root E naught minus V naught over the square root of E naught plus the square root E naught minus V naught quantity squared. So we can square that, where we've now replaced the energy of the incident particle, the total energy of the system to start with, is h bar k naught squared over 2m. Okay, so now what we have is, now we can calculate what the reflection coefficient is. The probability of its reflection depends on the energy of incidence that it has, and the size of the barrier, V0. Okay, now let's talk about the transmitted. So the transmitted, we could do the same thing. It's now it's a wave packet moving to the right after it's gone past the barrier. And we could put it into the integral and calculate the psi star psi, the probability density. But there's actually probably an easier way to do it, and that is that when this particle hits the barrier, then there's a probability that it's going to be transmitted, and there's a probability that's going to be reflected. And so those two probabilities, so the probability, we just calculate the probability of reflection, the transmitted coefficient is the same thing, using the transmitted wave functions, but the probabilities have to sum to 1. So the reflection coefficient plus the transmission coefficient is going to be equal to 1. Therefore, instead of solving the integral, we can just say that the transmission coefficient is 1 minus the reflection coefficient. And so we can put that in, and we have 1 minus square root of E naught minus the square root of E naught minus V naught over the sum of those two things squared. And so if we work it out, then we use the common denominator. We get E naught plus the square root of E naught minus V naught quantity squared minus E naught minus square root of E naught minus V naught quantity squared all over square root of E naught plus the square root of the difference quantity squared. Okay, so now we have to work out the algebra on that. And what you get is E naught plus E naught minus V naught plus the square root of E naught square root of E naught minus V naught minus E naught minus E naught plus V naught and then plus E naught times the square root of E naught minus V naught, all of that over this stuff squared. And so you notice that we get a bunch of stuff canceling, and we're left with, this is a, sorry, there's a 2 in front of here. So we get 4 times the square root of E naught times the square root of E naught minus V naught over this stuff squared. And so that is the transmission coefficient. Now we can calculate the probability that you would have a transmission, that the particle would actually transmit and travel on the other side instead of reflecting back. We can actually clean this up a little bit if we remember that C over A, using the initial energy, was 2 the square root of E naught over the square root of E naught plus the square root of E naught minus V naught. So then, what does that become? Well, the transmission coefficient now becomes C over A, that ratio squared, times the square root of E naught minus V naught over the square root of E. Or C divided by A, the square root of 1 minus V naught over E naught. So now we have relationships for the transmission coefficient, transmission probability, and the reflection probability. So now, based on the energy and based on the height of the barrier, we can now determine what is the probability that the particle is going to bounce back, and what's the probability the particle is going to go straight through, modified by the barrier. And the only thing now that is missing is those constants A, B, and C. So we've written them in terms of relationship to each other. But again, A, B, and C, those constants are essentially given by the initial conditions of how the reaction occurs. Okay, so in the next video, we'll proceed further and try another treatment of these transmission and reflection coefficients to understand the probability of what happens.